Okay, so your friend had an interesting question before you came. He was asking me how many hours do I expect you to spend on this course, preparing for the lectures. I think you should be spending something around 8 hours out of the class, preparing the pre-reports. Well, if you think of it, if I would be lecturing you like 4 hours to cover all the material. And I already know the material, so you should, but you don't. So you should be spending some more time trying to understand what the material is about. So that would say, well, let's say not 8, but maybe 6 hours the least. So that you will be able to learn on your own the majority of the material. There will still be certain things that you will not understand. Why does it do that? Certain steps, why doesn't it do it some other way, etc. And those are what makes your questions. And then when you come here, then after spending this, let's say 8 hours, you will think that you have understood the material. But then comes the questions of your friends, and you will realize that there were several things that you had missed. But of course, to have that realization, your friends should be asking questions. Well, you are the friend of your friends, so you should also be asking questions to help to make sure that your friends had learned the material. I get the impression that some of you are still doing the pre-reports in the way that you did in your first year. Well, most of them were my students in their first year, where they were also supposed to do the pre-reports, but there I didn't expect them to learn the material. I was expecting them to just skim over it. So that kind of takes, let's say, 1 hour skimming over the material, if they are willing to work. And then you just prepare the pre-reports, just a couple of sentences here and there, a couple of questions here and there, whether related or on. I mean, some students would also just look at the title of the chapter and prepare a pre-report. It doesn't work this year. So that year I was expecting you to spend like 1 hour at most. Here I'm expecting you to spend like 6 hours at least before preparing your pre-reports. Yes, now questions. Now, this time your questions can be on any subject that we had covered until now. How many of you spend more than 1 hour on preparing the pre-report? Except on the homeworks, I mean. The moment of inertia. Moment of inertia is a subject of classical mechanics, not of electromagnetism. Moment of inertia. Or dipole moment. Well, that will be a subject for next week. The dipole moment. The multiple moments, the dipole moment, the quadrupole moment, octupole moment, you will be studying next week. I mean, up to now, including your first year, a dipole moment we had only defined for a neutral system where you had a point positive charge and a point negative charge. But a dipole moment, all these moments you can define for any charge distribution. Even for a single charge, you can define a dipole moment. And you will study it this weekend, hopefully.
Divergence of the constant vector field is 0.
Yes.
And applying the formula, if you can, it's not 0. Del r squared del over del r.
R square vector field.
Hmm? So the vector field is r squared.
No, the vector field is, for example, k.
It's talking about the formula for divergence.
Okay. K vector.
Now it's divergence is del over d k r squared k.
Plus. Hmm?
Maybe have maybe have R nodes here. And R as a unit vector.
Hmm.
Okay. And we have the other components.
Yeah.
Okay.
Yeah. Plus 1 over r sine theta, del over del theta, sine theta, the theta component of k, plus 1 over r sine theta, del over del phi, phi component of k. This is the divergence of E. And your claim is that this is non-zero. Hmm?
We substitute to, we have KR is R dot K. We substitute into R.
Kr is K dot R.
That would be much simpler.
Yes.
Cartesian coordinates.
Well, it shouldn't make any difference which coordinates we use.
That's easy.
But he's not convinced that in spherical coordinates we get the same answer. Right? So he says that, well, kr, k theta, and k phi are constants. So the derivatives of k phi with respect to phi is 0. And the derivative of, well, k theta, I can take it out. What remains is the derivative of sine. Kr is a constant, so r squared kr, derivative with respect to r, that's also non-zero. So those derivatives are non-zero, so the divergence seems that it's not zero in spherical coordinates. Right?
Sum is zero.
Hmm?
Maybe sum is probably sum zero.
First of all, well, let's see. The k theta is constant if I take it out, so I get this derivative of sine theta, which is cosine theta. That second term brings a cosine theta over sine theta. The third term is 0. The first term doesn't contain any theta, so the sum is not 0. If what I'm doing is correct, the sum is not 0. So what is it that I'm not doing correct?
Is K theta constant?
Is k theta constant?
It's not.
Is it or not? Hmm? Because remember, k theta is k dot theta hat. So is this constant?
You can substitute into theta
Hmm?
the expression in Cartesian coordinates, which we have sine and cosine.
It is constant. It is even Cartesian coordinate, right? If
No,
I
you see,
constant question.
divergence of E is 0 in Cartesian coordinates. There is no problem with that. So it should be 0 in any coordinate system we use. And so in spherical coordinates, we look at the expression for in spherical coordinates. But then, well, k is a constant, so kr, k theta, and k phi is constant. Let's put a question mark over there. They are constant. If I take them out of the derivatives, what remains is non-zero. So I seem to have a problem here. So the only question mark I have is that is kr, k theta, and k phi constant, independent of r, theta, and phi?
They're constant.
Hmm?
They're constant.
Are they?
It's a product of two constants.
Okay, so let's say theta hat is a constant.
Yes.
Let's see. Well, let me not draw let me just look at the YZ plane. YZ, the X is outside. What is the direction of theta hat vector at that point? Hmm? So this is the theta hat vector, do you agree? Hmm? What is the theta hat vector over here? It's the y hat vector. At this point, it's the minus z hat vector. At every point, theta hat is a different vector. So theta hat is in fact a function of theta and phi. Similarly, r hat is a function of theta and phi hat is a function of only phi. Oops. Not even 10. None of them are functions of r. So k theta, although k is a constant vector, but k theta is still a function of theta and phi, because theta hat is a function of theta and phi. So you cannot take these k theta, k phi, and kr out of the derivatives. Showed explicitly that even in spherical coordinates, the divergence of a constant vector field is 0. Yeah, I will write it and put it in note to class. So this is kind of the problem. Even if the vector is constant, it doesn't mean that all its components are constants in a given coordinate system. If your coordinate system, if your unit vectors are not constants, then the components should also be non-constant, so that the dependence on the point of the components should cancel the dependence of the unit vectors on the position, on the components, on the position. Okay? So you see, k hat vector, let's say, is this vector. It is constant everywhere. But theta hat vector is sometimes this vector, it's sometimes this vector, it is sometimes this vector. So the projection of this constant vector on theta hat is not constant, depends on where the theta hat is points. And theta hat, the direction of theta hat changes depending on your position. Not r, but theta and phi.
Also, in spherical coordinates, we interpret vector r as r times r hat. But we can also write it as r times r hat. Component of, I mean, there's no phi and theta.
No? It is 0 in the phi hat direction, 0 in the theta hat direction. Because r hat at a given point is defined to be the unit vector in the direction of the position vector. This is kind of the definition of R hat. There are no theta or phi components.
So definitely whenever we try to move from the Cartesian coordinates to the spherical coordinates, we will only have R.
To write the R position vector, you only have the R hat vector. If you have some other vector, well, it can have any all three components.
Can you give an example?
This one, you see, if you write it down, again only in the YZ plane, let's say the K vector is this constant vector field. Let's look at this point. At that point, this is how we define the R hat vector. And this is how we define the theta hat vector. So this vector, K, both has components, this KR, and also K theta.
So whenever we evaluate our vector field at the origin, its spherical coordinates is just R. But otherwise it will have...
No, which vector you mean? Well, on the origin is along the z-axis, let's say in general. These unit vectors are not so well defined. Z-axis is a singular, is a collection of singular points. In the sense that you see along the z-axis corresponds to theta is equal to 0. But if theta is equal to 0, just rotating around the z-axis, nothing changes. So how do you define the phi hat along the z-axis? Because phi hat is basically a vector that goes around the z-axis. If you are right on the center, it's kind of difficult to define the z-axis, define the phi hat. So talking about this k hat in the origin, what is also r hat at the origin? You see, r hat we always define as r over r. But at the origin, r is 0. So you cannot really define an r hat on the origin.
When we have a vector field, we input the coordinates, and we get the vector.
Mm-hmm.
So if we evaluate it at the origin, R will not be 0.
If you evaluate,
R, the vector itself.
the vector itself will not be 0. But the spherical coordinates at the origin, they have this singularity at r is equal to 0. So that's kind of the problematic. So if you are very interested in what happens at r is equal, well, and we will see cases where if your function is 0 at the origin, no problem. But if your function is non-zero at the origin, you start getting problems. What do you mean by r hat vector at the origin? Or what do you mean by phi hat vector along the z-axis? That's not really uniquely defined. You should better have the phi hat component 0 to avoid the ambiguity.
Can you derive the energy density for the electric field? It's not very clear.
What is not clear?
How we assume that the electric field itself has energy density, not the charge.
Mhm.
How we try to-
So what is the, given the charge distribution, how can we write the energy of this configuration? Suppose we have the rho We know the rho, let's say we know the potential at every point. These things we have evaluated. So what is the energy density of this configuration?
Four times, 5 times, volume.
Is this it?
Energy stored in the system.
Now let's give it a try. Let's see. I mean, if you have hard time remembering some of the expressions, you can just try it for simple cases. Let's say rho of r is equal to Q1 Dirac delta at r minus r1 plus Q of 2 Dirac delta of r minus r2. So we have these 2 point charges, one located at r1, the other one located at r2. And what is the energy of this configuration? If you put it in the above expression, you get the energy density. Energy is equal to Q1 phi of r1 plus Q2 phi of r2. What is phi of r1? Well, phi is created by the other charge, so it is Q2 over R1 minus R2 plus Q2 times what is the potential at the position of R2? Q1 over R1 minus R2. So it was a good try, but we have this twice Q1, Q2 divided by R1 minus R2. Oops. So there's something wrong in that expression of the energy. How can we correct it?
Using coefficient 1 over 2.
Exactly. This is the solution. Why do we have that 1 over 2? Okay, in the simple case we see that, but... Yeah, we are double counting, kind of. You see, for a given charge, we are counting it both once that it is in rho, so it is the charge multiplied by the potential created by the other charges, but that charge is also creating phi. So we have the other charges multiplying the potential created by this charge. So we are kind of double counting. That's why here, exactly look at here what happened. We have the charge Q1 multiplied by the potential, but Q1 is also creating the potential on the other charge. So that's the second place where we are calculating the contribution from Q1. So we should divide by 2. Now, if we divide, this is our expression. Now, of course, we want to express these in terms of the electric fields. Well, phi, we know that its derivative is the electric field, so it's not so easy to express phi in terms of the electric field. We have to input some integrals over there. If necessary, we can do that, but we can do it more easily on rho. We can write rho as the derivative of the electric field itself. And what's the relation between rho and the electric field? Divergence of E is equal to 4 pi rho. Or rho at a given point is equal to 1 over 4 pi times the divergence of E. Well, let's put it over there. E is equal to 1 over 8 pi divergence of E times phi. Well, it would be nice if we could move that derivative to the potential, because the derivative would give us the electric field. And we can change what we are taking the derivative of by using integration by parts. Let's say this is equal to 1 over 8 pi del IEI times phi. This is equal to 1 over 8 pi del EI of phi minus EI del I of phi 1 over 8 pi del EI of phi plus EI squared, because the derivative with respect to xi of phi is nothing but the xi component of the electric field with a minus sign. Well, let's write it in a more familiar form. This is the, well, here we have a vector field. We are taking its, let's say, x component, taking the derivative with respect to x, and taking the y component and taking the derivative with respect to y, etc. So that's the divergence of that electric vector field plus E squared over a given volume. One over 8 pi, the integral of E squared d cubed r over some volume plus 1 over 8 pi times at the boundary of the volume of phi times E. This is the energy. Well, let's see, what is this volume? We are calculating the energy of all the charge configurations, so it should be some volume that contains all the charges, rho. But if we make it larger, well, we can make it larger because outside of our charged region, rho is 0. So if we change the volume, enlarge, I mean, let's say if the charges are over here, that just means rho of r is non-zero only here. So we can take this volume integral to be this volume or this volume. The difference, but in the region where we have this difference, rho is 0. So we are not really changing anything. So you can just take this volume to infinity. Then the electric field just becomes 1 over 8 pi the integral of E squared over the all of the volume. So we can write the energy density in two different forms. One will be in terms of the charges and the potential. The other one will be in terms of the electric field. Now, when we study electrodynamics, when we are looking at dynamics, we will see that we cannot really define a function of potential in the sense that this will be our energy. We cannot really define it. But nevertheless, we can, even in electrodynamics, we will be able to talk about the electric field, so this definition will still make sense in electrodynamics also. Mm-hmm.
How do we relate this to the pointing vector? Because we have problem with the units.
Well, what's the pointing vector?
Pointing vector is the one that the energy flux.
Well, let's see, what do you mean by flux?
Energy per unit area, energy deposited from the electromagnetic wave.
So it's flowing, right? Is it static? Is it static?
No, but it's
No. Is it related with the magnetic field also?
Yeah.
What's the magnetic field? We are in electrostatics. Yes. Now the units will match. The problem is which units are you using? In these units I don't have epsilon zeros, etc. But I'm just using different units. We will see when we study, after we complete magnetic fields and we are looking at dynamics, we will see the pointing vector, the flux, etc. But the trick will be basically the same. You see, here actually what we are really doing is that, you see, this is nothing but the work done on the charges. So where did that work come from? It changed the energy stored in the electric field. Right? So in a sense, this expression is the change in the energy of the charges, and this expression is the, in a sense, when the charges, let's say they go to infinity, the electric field will be zero. So this is the change in the energy on the electric field. Since energy is conserved, they should be equal. And they are equal. In fact, when we are talking about more general energy and momentum conservation, that is what we will be doing. We will look straight at the, let's say, the energy of the charges, studies their change, and relate it to a change in the electromagnetic field only. And then we will claim that, okay, so this is the energy of the electromagnetic field. So since the change in the mechanical energy of the charges will be equal to, with a minus sign, the change in the energy of the electromagnetic field, or change in some quantity of the electromagnetic field, we will identify that something as the energy of the electromagnetic field. So you see, energy is some kind of a, okay, quite often the students ask, what is the physical significance of energy? Not much really. In the sense that it is a way that we are just keeping track of certain terms. It's kind of an accounting. So that is what we will be doing over here. We will see, okay, some property of our particles have changed, and then we will show that the same property of the electromagnetic field is changed by some other property of the electromagnetic field is changed by the same amount. So we say, okay, so that is the energy. So just sum them up and it is conserved. And also in the way we define it, we define the energy so that the forces, etc., acting on the system are always such that they are trying to minimize the energy. So there was a question about why is the energy minimum? Why does a system behave as to minimize the energy? Yeah, that is the definition of energy. They say potential energy, mainly.
So is that a real question?
Not really. Now the question can be, why is there such a quantity? Well, it depends. I didn't allow him to ask something on electromagnetism, magnetic fields. And if you ask me about sports, no, you can ask. You cannot ask it. Try it.
According to some physicists, it's said that the energy of the universe is increasing, right?
No.
One, I heard it.
No.
Yeah. So is it true?
I mean, I never heard of such a claim. The velocity of the expansion is increasing. The energy of the universe, as far as we know, is zero. Consistent with zero. The total energy.
We talked about the field forces and how they are actually particles. Momentum of particles emitted from, let's say, an electron. And so, how did we? I didn't understand how we related to the conservation of energy and what's it, Heisenberg uncertainty test.
Did you understand the question? Hmm? Hmm? Okay, you should ask him that. Hmm?
So we said that if we have a force due to a field that is centered at some point, that point is emitting particles. But these
Do you agree?
particles-
So do you remember that? Did we say that?
We said that.
I'm asking them.
No.
Hmm?
Yes, yes.
In which class?
This course.
In this course.
Yes.
No, I'm also trying to understand whether they were listening or not. I mean, they are not speaking, but I have doubts that they are listening. So we did say that, but they didn't hear it. So, I mean, can you repeat the argument again?
Okay, so we said that if we have a field force, this force comes from centered at some point. This force is due to the momentum of particles coming out of that point, emitted from that.
Did you understand it?
It's related to quantum.
Hmm? Yeah, that is the opening chapter of your book. Right?
So we said that how doesn't it violate the energy conservation? And we somehow related it to uncertainty constant.
It was just a summarization. It was not the fact.
Well,
It was for the purpose of teaching the concept.
Well, it is a fact as far as we know. I mean, that is the way we describe the forces now. That's our modern understanding of the force. Every force is due to the fundamental forces that we know are due to exchanges of other particles.
That goes into quantum.
Sure. But that was in the book. And you are learning quantum physics, right? Quantum mechanics, Devon. Physics or mechanics? Physics. Quantum physics should be enough to answer his question. So this was the question. So we have these two charges, Q1 and Q2. Now, forget about Q2 for the time being. Q1 is constantly emitting and absorbing photons. It's a constant process. So if you bring this charge Q2 nearby, some of the photons will be absorbed by Q2. And this photon has some momentum, let's say P. So the momentum of the charge Q1 will be changing by minus p, and the momentum of the charge q2 will change by momentum plus p. And remember, the force is nothing but delta p over delta t, the average momentum change. So this is basically how the charges exert forces on each other. This is our modern understanding of the concept of force. We don't really talk about forces anymore, but we talk about particle exchanges. And so now the problem is, we have this charge which initially it has some momentum, let's say large p, then it has a momentum large p minus p because it emits a photon with momentum p. So you have your charge over here. Well, its momentum changes, so its energy changes on its own. Furthermore, the photon, let's say, you can conserve the momentum, no problem with that. P is equal to P minus P plus P. This is the energy of the photon, this is what remains to the electron, to the charge. But if you try to write the energy of the, let's say, Q1 with momentum P will not be equal to energy of the charge Q1 with momentum P minus P and plus the energy of the photon with momentum P. You cannot satisfy this relation. You cannot set it equal. So what happened to energy conservation? Well, since you didn't listen in the first hours, I will just answer it. You see, we also know this time-energy uncertainty relation. So energy conservation means that we definitely know the energy so that we can compare it. That is, delta E is equal to 0. But to definitely identify the energy of a given state, you need at least a delta T amount of time. That is infinite amount of time. But that is not practical. So you cannot exactly determine the energy of a particle in practical terms. Or you can say it in another way, delta E can be non-zero. You can violate energy as long as that violation doesn't last long. How long? Well, it should last at most as much as delta T. If there is an energy violation of delta E, it should disappear after a time delta T, more or less. So here, does it disappear? Well, yes. I mean, you see this photon is eventually absorbed by the other charge, and you can have the energy of charge Q1 with momentum P, let's say 1, plus the energy of the charge Q2 with momentum P2 equal to energy of the first charge with momentum P1 minus P and energy of the other charge with momentum P2 plus P. So once the other charge absorbs it, energy is conserved.
What if it's effective for
Let's say, how long does it take the photon to go from charge Q1 to charge Q2? Well, let's say the photon travels at the speed of light. Well, these are weird photons. They need not travel really exactly at the speed of light, but let's say they travel at the speed of light. That's the maximum speed. So the largest distance they can go will be proportional to their separation. The time they go will be proportional to the separation. So if the separation is large, then it will take a long time for the photon to go from the charge Q1 to the charge Q2. But to conserve energy, the photon should go from the first charge to the second charge. After the second charge absorbs the photon, we can have energy conservation. So delta ET becomes very large if the separation is very large. Well, if delta T becomes very large, that means delta E should become very, very small. The energy violation should be very small. Is it possible for a photon to have a very small energy? What is the lower limit of the energy of a photon? This is your modern physics question. What is the energy of any particle? That is non-relativistic case. What is the mass of a photon? It's massless. So the photon can have as small as energy as possible. So delta E can be very small. So allowed delta T can be very large. And the photon in that amount of time can travel a very long distance. So the electromagnetic forces just can influence, two charges can influence each other over very large distances. Basically, its range is infinite. But we also have other forces like the weak force. These are the subnuclear forces. But weak force, they have the corresponding mediator particle, the W and the Z bosons. They are like 80 times heavier than the proton. Well, if they are 80 times heavier than the proton, you see the minimum energy that a particle can have is its rest mass energy. So if a particle emits for a very short amount of time a W boson or a Z boson, the energy violation is huge because the mass of the W is huge. So delta E is huge, but that means delta T should be very small. If delta T is very small, even if they travel at the speed of light, they will travel a very short distance. So weak forces cannot influence at large distances.
So the power of R is less than -2.
No, the power of R is always -2 because that is the inverse of the area of a sphere. For any particle, but for the other particles, the potential doesn't go as 1 over R, but it goes as e to the power minus m R over R. It decays exponentially. Again, h bar is equal to c is equal to 1. So these particles have a range, these forces are said to have a range of 1 over m. Now, if you want to put in the h bars and c's, h bar over mc. This is the range of a force if the force carrier has a mass m.
Neglecting the energy due to the motion. Getting the kinetic energy. This is just the rest mass.
Yeah, I mean, typically the range, I mean, when you say, okay, the range is 50 microns, you don't really mean that at 51st micron it goes to 0. So it's just kind of at 50 microns, the magnitude has diminished significantly. So even at 50, 60 microns, there will be some force, but it will be very small. If you add any corrections to this, I mean, okay, maybe not 50, but 51 or 49. Doesn't really make any difference.
So what if we try to block these photons from the electromagnetic wave?
Such as? How do you block photons?
With some material.
Such as? What kind of material do you use?
Black
Oh, let's say a conductor. You put a conductor. It will absorb the photons, right? Well, you had already studied the, let me draw it a different way. This is your infinite conductor. You want to block it completely. So what is the electric field here created by the charge Q? Let's also ground it. 0. So if you block the photons, the other charge doesn't feel any force.
If it's not infinite.
Hmm?
If it's not infinite.
Then there will be some electric field, but the photons can also go around it if it's not infinite, so you're not completely blocking it. So then that's another confusing thing about this photon exchange. I mean, you always tend to think that the photon exchange is straight in that direction. So if it is moving in that direction, then it has to carry a momentum in that direction. But so how come there is an attraction? Yeah, there comes the quantum mechanics. If you are talking about the definite momentum state, it's not just this blob of energy moving in that direction. That momentum state is everywhere. So if you put a finite barrier, it can just, there will be diffraction around the edges. So that wave will eventually reach the other charge. Or if you want to talk about localized packets, then those localized packets don't really have a definite momentum. So they're just superpositions of all possible momenta. Okay, let's go back to our main subject. It was an interesting diversion. Let's come back. Now, the things we had covered, the potential of a continuous charge distribution, how to calculate the electric field of a continuous and discrete charge distribution. We had studied the method of images.
The direction derivative of 1 over r squared with the direct alpha. Direction derivative of 1 over r squared.
What do you mean by directional derivative? The divergence of r hat over r squared.
Direct alpha.
This is 4 pi times the direct alpha.
It is really good.
So do you agree that divergence of r hat over r squared is 0? Okay, you don't agree. Let's show it. Divergence of r hat over r squared. Now we had already written the divergence of any vector field was 1 over r squared del over del r squared e, er plus the other ones. This only has er. So this is equal to 1 over r squared d over dr r squared of 1 over r squared. Well, 1 over r squared times r squared is 1, derivative is 0. But of course, we can talk about the derivatives, etc., at every point except when r is equal to 0. The problem here is kind of we have this boundary. When you are taking the derivative, when you are defining the derivative, you usually take the limits as r some limit as r goes to 0, but that limit should be in both directions. But we cannot really talk about going to r taking the r equal to 0 limit from negative values. That doesn't make sense. So that's basically one of the reasons why we cannot really trust this result that r is equal to 0. Now we should look at something else to determine what the value is at r is equal to 0. And to do that, what we do is we look at this integral. So this is our r equal to 0 point. Well, we just take, let's say, a sphere of radius r. Okay. And we know the divergence theorem, so we can convert this into a surface integral over the boundary. And this turns out to be 4 pi. So this is kind of del dot r hat over r squared is equal to 0 if r is non-zero, but its integral is finite. Over a volume containing r is equal to 0 is finite. It's equal to 4 pi. So it is this weird function that it is 0 almost everywhere, but the integral is finite. And that is what we define as the Dirac delta function. And this Dirac delta function is that weird function. You can say that this is kind of the definition of the Dirac delta function. Dirac delta of r is 0 everywhere except when r is equal to 0, and its integral over a volume containing r is equal to 0 is 1. So that is how we define the Dirac delta function. And this divergence of r hat over r squared satisfies all these properties. Well, its integral is not 1, just 4 pi, so we multiply the Dirac delta by 4 pi. Let's just check another thing. X, Y, and Z. Let's consider this point and this point. The points, let's call this R plus, this point R minus. R plus or minus there along the Z axis, plus minus, let's say epsilon Z hat. Epsilon very small. Is the electric field continuous across the surface? Well, xy plane is a surface. As we cross this point, is the electric field, does the electric field change continuously as we cross the origin? We cross the origin by taking the point, let's say dr is equal to dz squared, and we take d, let's say, from plus epsilon to minus epsilon. D goes from plus epsilon to minus epsilon. So does the electric field change continuously? At this point. You see, what is the direction of the electric field at R plus if it's a positive charge? Plus that direction. This is the electric field at the point R plus. So as R plus approaches the origin, does it change its direction? No. It's always in the positive z direction. What about at R minus?
Negative.
Negative. So is the change in the electric field continuous as we go from R minus to R plus? No, there's a discontinuity. But if there is a discontinuity as you cross a surface at a given point, that means there is a surface charge at that point. Well, this is a point charge, but nevertheless we can imagine that there is a surface charge density on the xy plane, but the charge density is zero almost everywhere except at one point. That's also legitimate. So this tells us that there is some charge density at the point, at the origin. Now, the funny thing is, if let's say if you take R plus to R minus along this line, and so you cross the surface, let's say the xy plane, at this point, does the electric field change continuously?
Yes.
You see, here we have the charge. So we are just looking at how the electric field changes as we go from that point to that point. I'm imagining that there is this surface. And I'm looking at the discontinuity in the electric field at different points on the surface. Here is my charge. If I want to look at the discontinuity of the electric field at this point, what I need to do is, let's say we start from one side of the surface. We change that point slowly. Now we reach the surface. We cross the surface and go to the other point. Now, this crossing point, does the electric field change continuously? Yes, because there's no charge over there. But if I cross it along this line, along the z-axis, it changes discontinuously at this point. Then I say that there's a surface charge at that point. We will do some other examples where we will be treating these point charges as surface charges. Because it's kind of a surface charge, but the charge density, the surface charge density is non-zero only at a point on the surface. Or we can even call it a linear charge density, if you like. Just imagine any line that passes through the point charge, and then we will say that the linear charge density is non-zero only at that point, and it is zero everywhere else. Those are all valid descriptions. And if any one of those descriptions suits your purposes, pick it up. Yes, other questions? Well, your friends were asking hundreds of questions, Emre. Now you have to pick it up.
So when we use the dehydrator, we assume infinite charge at a point. But of course, this is an approximation
No?
because there is no infinite charge. Even Einstein has done it.
Are you sure?
The way the process
Well, you see, saying an object is a point already tells you that it has infinite, if it has a mass, it has infinite mass density. And if it has a charge, it has infinite charge density. Now, is the electron a point? Does it have a size? Well, experimentally, we couldn't measure a size of the electron. We could measure distances of the order of 10 to the power minus 18 meters. And up to that distance, the electron does not seem to have a size. Well, it might have a finite size smaller than that one, but to the best of our knowledge, it doesn't have a size.
Still, its position is not.
So? Yeah, that is another issue. And does its size or exact position has any meaning really? But classically, we can speak about the position. We might not know it, but we can say that it has an exact position. Now, quantum mechanically, of course, things start to get a bit problematic because the electron doesn't have a definite charge. There is a wave function, but so should the electric field. So all this description already needs to be somehow modified.
Yes, you are classical. Classical.
Electron is a point.
When we have a surface, a charged surface.
Electron.
A charged surface or
Okay.
a conductor, let's say. So we say we have some finite charge density at the surface.
Okay.
Right? So one question. So when we use the data, it's just an approximation.
No. Okay. Let's look at the problem of the surface charge. We are talking about ideal conductors. And when we are describing the conductor, we are assuming it's the continuous media. It's not a discrete media. So when we are talking about a conductor, it's not really made up of atoms. It's the idealization. Of course, it doesn't work if you just look at the microscopic properties, but if you look at the macroscopic properties, the general properties, it works. So in a conductor, the electron we are treating the electron kind of as if it is just spread out. So there is an average. When we discuss the electrostatics in matter, it will be more clear. There we will explicitly specify that we are looking at the average electric field. It will make more sense then. Because typically if you have this, let's say the more realistic picture, the charges are not at the surface. There is a thickness of place where your charge density will be non-zero, the average charge density. Now, in quantum mechanical description, I mean, the only thing you can actually talk about the averages. Now, the electron is a point charge, but the average charge distribution corresponding to an electron is not a point because of the spread of the wave function.
Actually, I'm asking this question because I want to know the order of magnitude of this figure.
Well, it depends on how you are probing it.
Depends on how I am
Probing it. Typically, you would say the electrons are always on the atom, right? They're attached to the atoms, kind of.
So it's a conductor. It's not.
Well, nevertheless, it just jumps from one atom to another atom. Yeah, we will have this concept of skin depth eventually. Not yet. Well, skin depth will be more related with electrodynamics, but I'm sure it's also related with what we have over here. I mean, for example, here, well, that thickness would probably be related with the conductivity.
What the temperature?
Conductivity depends on the temperature. And it might also depend on the temperature independent of the conductivity. An ideal conductor that we are discussing here is which has an infinite conductivity. So I would say that thickness is kind of the inverse, proportional to the inverse conductivity. So for this ideal case, it is 0. In a realistic case, it won't be 0. Of course, as you increase the temperature, you would expect that thickness to get larger and larger. But the problem with that one is the temperature doesn't really affect the electrons that much. Typical temperatures. Unless you reach such high temperatures that you are close to the melting point. Anyway, those things you will study in 430. Statistical thermodynamics. And the more realistic description you want, the more complicated it becomes, the more effects you have to take into account. So that's why in this semester we will be sticking with simple systems.
If you have the deep field and double snip, like a double snip experiment, what will be the result?
Is it electrostatics?
It is.
So you are saying this one. So we have this conductor. Is it grounded?
Yes.
This one is also grounded. Let's say this one is also grounded. And you have a point charge over here. So what will be the field everywhere? Is that your question? I have no idea.
For this, if we use the photon model, or if we use
But photon is definitely not electrostatics. So this should be
It should not-
electrostatics. Should it? Or do you also have a, let's say, a conductor over here? Do you want it? Or not?
To see.
Hmm?
I don't know.
Okay. So what will be the electric field on the other side? Well, the problem here is, let's say,
Is it
hmm?
equal to conductor or something like
Well, you can take it to be finite and then take the limit that it's very thin. Or you can take it to, you can keep it finite. Well, you have the first region, you have the second region. You have to solve for the electric field in the first region, the electric field in the second region.
the third one will be in the middle.
Hmm?
Third one will be in the middle.
If you give it a finite thickness, then impose boundary conditions.
See, the boundary is mixed.
Hmm?
The boundary is mixed.
Well, boundary conditions would, my boundary is this slit over here, this metal, and this one. And another question, are these, of course you have to take into account whether these slits are they infinite strips of metal, or do you have a continuous metal, and you have some, a circular opening, because the cross-section of that will also look exactly like this, but I think it should be better if you just take this infinitely. Now the boundary condition, the potential should be 0 over here, 0 over here, 0 over here, and it should be, the electric field should be, no, the potential should be 0, 0, and 0. Well, it might have some other value over there, not necessarily 0.
Assuming no other charges, we can calculate it from this charge.
Yeah, it will be a long computation, but hopefully it will be doable towards the end of the semester. Towards the middle of the semester, it should be doable.
Can't we do it already? Using Green's theorem.
Well, you see, Green's theorem, of course, but you have to first solve this problem to use the Green's theorem. Because the Green's theorem tells you that you should first calculate the Green's function. Well, Green's function is the solution of a point charge to this one. So once we solve this one, then we can solve any other kind of potentials at those at those conductors. So Green's theorem doesn't really help for point charges, because to be able to use it, you first have to solve the point charge problem.
What about separation of variables?
What is that?
What's some equation?
What is the separation of variables?
We have the differential equation.
Yeah.
Wilson's equation.
Okay, so we didn't discuss how to apply it to electrostatics yet.
It's in this chapter.
Hmm?
It's in the chapter that we read.
No, that you will be reading. No, not even that one.
It is in the
In this
chapter
one?
that we read.
No. In this chapter, you have only the method of images.
We have it.
No, find it.
It's for the class application.
Hmm?
For the class application.
Okay. Where is it? Oh, here. Okay. Mm-hmm. Yep. Then you can.
And there are a few lines in this that I didn't understand.
Hmm?
There are a few lines in this problem that I didn't understand.
Ask.
So when it says So after the separation of variables, we got two equations. One of them is Euler's equation.
Mhm.
And this allows, because we have an undetermined constant from the separation variable. So this, depending on this constant, we find the powers of the solution
Mhm.
in the solution of Euler's equation. Then the rule says, because the function is unique, because the potential is unique, these powers should be integers.
Mhm.
Do you understand that?
Which problem are you? Okay. So we are talking about this problem, right? We have the metal, then there's this angle beta, we have a point charge somewhere over here. Let's study this problem. We already discussed this using the method of images. Let's do it by what's called the separation of variables. Now what we do here, okay, first of all, we can solve this problem. I will assume that I have a boundary over here. So here is our boundary. And this plus q charge is on the boundary. And this distance, let's just call it capital R. Also take these are planes. So we basically have this configuration. We have this metal surface, this other metal surface. They are brought together, but making an angle. And they extend them up to infinity. The point charge is somewhere over there. So what the best choice would be, in this case at least, the cylindrical coordinates. You can use any coordinate system you like. The problem will be, the motivation for choosing one coordinate system over the other one would be, how do you specify the boundaries? You do want to simplify your definition of the boundary. For example, in this configuration, I have this boundary, and I can specify those boundaries. Let me choose my, let's say, z-axis is perpendicular to the screen. Let us say this is my x-axis, this is the y, so this is the z. Now, my boundaries are specified by these equations. Phi is equal to 0, phi is equal to beta. Phi is equal to 0 is this boundary over here. Phi is equal to beta is this boundary over here. They are just simple equations. And this boundary over here is specified by rho is equal to r. These are the three boundaries I have. Now, you can use Cartesian coordinates if you want, but it will be complicated to specify your boundaries. For example, this boundary will be x squared plus y squared is equal to r squared. It depends on more than one variable, and it will complicate your life. So the less variables your boundary definitions contain, the easier the problem it will be to solve the problem. So in cylindrical coordinates, except at the boundary, Laplacian of phi is equal to 0. Because my point charge is on the boundary, well, there might be surface charges on the phi is equal to 0 and phi is equal to beta. So just except inside my volume, not on the surface, there are no charges. So the Laplacian is equal to 0. So this is the equation I need to solve. Let me also call this one region 1, this region 2. And, well, these are grounded. Laplacian of phi is equal to, in cylindrical coordinates, this is 1 over rho, del by del rho, rho times del phi by del rho, plus 1 over rho squared, del squared phi by del rho squared, plus del squared phi by del z squared, this is equal to 0. Now, the idea of separation of variables says that, okay, phi, which will be a function of rho, phi and z, well, okay, bad notation, let me make this capital phi. That's not the coordinate phi. My potential will be a function of rho, phi, and z. Let us try to find a solution which can be written in the form of a function, the product of a function that depends only on rho, another function that depends only on phi, plus another function that depends only on the coordinate z. This is our assumption. Or let's say trial. Now, if you put it in our equation, del squared phi, and let us also divide by our potential. If you do the algebra, what you obtain is 1 over rho, d by d rho, rho times dr by d rho, plus 1 over rho squared, sorry, this is phi, d squared phi by d phi squared, plus d squared z by dz squared. This should be equal to 0. And here we have the 1 over r, here 1 over phi, here 1 over z. These are the equations. My equation just becomes this one. Now let's look at the last term and these terms. The first two terms depend on rho and the coordinate phi. The last term depends on coordinate z. And doesn't depend on rho or phi. But this tells me that I can look at the potential at the points that have different z values but the same rho and phi. I have infinitely many of them. As I change z, the last term, the value of the first two terms do not change. So the value of the last term also should not change. So the last term should not really depend on z. It should be some constant. So let's just call that constant. Let's call it kappa, or kappa squared. I'm just giving it some name. What is kappa? I don't know. It's just some constant. I know that it should be a constant. I'm just giving it a name. Now let's look at the other terms. Then del squared phi over phi. This just becomes 1 over r, 1 over rho, d by d rho, rho times the derivative of r with respect to rho, plus kappa squared, plus 1 over rho squared, times 1 over phi, del squared phi by del phi squared. Now I will basically do the same thing. Just look at this term in parentheses. It depends on the coordinate phi. And nothing else depends on that coordinate phi. So this should be 0. So as I change my coordinate phi, well, since the other parts, this 1 over r squares or the derivatives with respect to rho, etc., they do not depend on phi. They do not change. If this equation is to be satisfied, so phi shouldn't change. That term in parentheses also should not change. So that tells me that 1 over phi, d squared phi by d phi squared, should also be some constant. Let me call it minus m squared. And I am left with this equation now. plus kappa squared minus m squared over rho squared, this should be equal to 0. So I have my three functions, and I know the three equations that they should satisfy. Now, there are a couple of things that I have to pay attention to. You see, this function phi, if I take this coordinate phi, add 2 pi to it, I should get the same value. Because if you have one angle, if you add 2 pi to it, you are exactly at the same point. And the value of your potential should depend on your point, not on which value of phi you pick, if your function is to be single value. Because if this is not satisfied, then although you are at that point, the value of your potential will depend on whether you prefer to choose that angle between, let's say, 0 and 2 pi, or between 2 pi and 4 pi, etc. Then its value will be different in each case if this is not satisfied. So that's not what we want. In fact, that is the reason why I chose this sign to be minus, because I want this phi to be periodic. So this tells me that phi, well, that is probably the easiest equation to solve. Phi should be equal to A times cosine m coordinate phi plus delta. Or let me say sine m phi plus delta. A and delta are some constants that I do not know. And they can even depend on m. So I have, in fact, many functions that satisfy this condition. That depends on m. Well, there will be many functions, here, I already know, well, in the z direction, there is no periodicity. That is why I chose this sign to be positive, because if I had chosen it to be negative, it would just give me a periodic function. But there is no periodicity in the z direction. So that's why I chose it to be plus. So there's z, now this is phi, coordinate. The z function is a times e to the power I kappa z, no, not I, plus kappa z plus b e to the power minus kappa z. Depending on the value of k.
To simplify the problem, we may take z equal to 0. And therefore, we can just neglect.
Well, not really. I cannot take, depends on what I am interested in it. You see, I have these plates connected at some angle. I have this point charge over here. Do I want the potential at these points will be different than the potential at this point. So that's what I also want to study. As you change z, the potential will change. Now there's a problem though.
We may take a two-dimensional problem.
Well, if I convert it to a two-dimensional problem, then what I am actually studying is I have these plates and I have a linear charge density running through the z-axis. Now it will be easier. That's for sure, because then I would say, well, there's nothing depends on z, so this function z should be just a constant if it's a linear charge density. Now I am facing this problem that, you see, if this solution goes to infinity either at plus z or minus z goes to infinity, the potential should be finite everywhere. And as we go to infinity, it should go to 0. So what I should do is that Here is my charge. I already separated into these two volumes. I should also separate it above z and z equal to 0 and below z equal to 0 because the solution will look different in both cases. But in any case, the z will be actually a times e to the power minus k absolute value of z. So this is kind of, I separated into two regions. I know that everything is symmetric under z goes to minus z, so the potential should also have that property. So that's why, and this solution goes to 0 at infinity. And so there's, I already solved two of my three equations. Then I have this third equation. Well, this one over here. And the solution will depend on kappa and z. Then this phi dependence depends on m. Z dependence depends on kappa. Sorry, kappa and m. All these are possible functions. So at this point, there is no reason for taking a particular value of kappa or m. Sum over all possible values of kappa and m. This is my phi. Well, this is a general solution of the Laplacian in spherical coordinates. Well, there is another catch. I will solve this phi in region 1 and in region 2. So I will have these coefficients difference in region 1 and in region 2. Region 1 and region 2 have different r's because region 1 I call the region rho less than r, and region 2 I call it rho larger than r. Now I have my phi. The next thing, I know that phi should be continuous between these regions. But the continuity just tells me that r, k, m, 1 at the distance r should be equal to r, k, m, 2 at the region r. It's their coefficients. So this is one condition on my two sets of C's. The other one is the discontinuity in the derivative of phi with respect to rho. Is it at the boundary? This is another boundary condition I have. So is it continuous or discontinuous? Let's say this angle is phi 0. Well, it should be continuous at every point except then if phi is equal to phi 0. Because here I have my boundary surface. There is no charge except then at the point phi is equal to phi 0. So this should be equal to 4 pi times q times Dirac delta phi minus phi 0. Maybe some other coefficient. That should probably be 1 over r or something like that. I don't know. This is the surface charge density at that point.
Say something about the equilibrium.
This is my surface charge density. And what else do I have? I know that phi, the potential when the coordinate phi is equal to 0, should be equal to 0. But this tells me that, let's say, just look at this phi dependence. Sine, when phi is 0, there is no m dependence. Sine of delta m is equal to 0, which tells me that delta m should be 0. There are no phases. And what else I know? I know that the potential at phi is equal to beta should be equal to 0. But this tells me that sine of m times beta should be equal to 0. Or m, up to this point, m was kind of arbitrary, but m should be just pi, a multiple of pi over beta. Let's call that n. Otherwise, this boundary condition will not be satisfied. So we already have a general expression of our potential as a function of rho and phi and z. This is equal to sum over all possibilities. Well, here I have a sine of m over beta and phi, the coordinate phi. Then I have e to power minus kappa of z. Well, then I have the solution, the radial solution, as a function of n and this kappa with suitable coefficients in region 1 and region 2. This function already satisfies the boundary conditions on the plates. The boundary conditions on R2 should go to 0 as rho goes to infinity. At infinity, we can set the potential to be 0. And R1 should be finite when rho goes to 0. And we also know how to match R1 and R2 at the boundary. And these will be enough to determine what these coefficients are. Now, in the book, they are more interested what happens when rho goes to the rho very small. Now, when rho is very small, let's go to the equation. So this is our equation. Let's just expand it a bit. So this is 1 over rho times rho times the second derivative of r plus the first derivative of r plus kappa squared minus m squared over rho squared times r. This should be equal to 0. d squared r by d rho squared plus 1 over rho dr by d rho plus kappa squared minus m squared over rho squared r equal to 0. This is the equation we have. Well, you see, when rho goes to 0, the kappa term will be negligible because m squared over rho squared will be huge, close to rho. So close to rho, the solution will behave like close to rho equal to 0. We have the rho squared, d squared r by d rho squared, plus rho dr by d rho, minus m squared r equal to 0. What is the solution of this equation? Rho to the power, let's say, nu. For such a solution, if you put it over here, you get nu times nu minus 1 rho to the nu plus nu times rho to the nu minus m squared rho to the nu. This is equal to 0. We can cancel the row to the nu's. We have nu squared minus m squared is equal to 0. And nu is equal to plus or minus m. But we want a solution that is finite at nu is equal, or rho is equal to 0. So finite solution is r is equal to rho to the power m. Well, the problem is what happens if m is small, let's say. M is 0. Can we set m to 0? You see, let's go back. M determines our angular part of the solution. And we said that the angular part is this one. M is equal to pi over beta times n. If m is 0, that means n is 0. If n is 0, sine is 0, so there's no contribution from that part.
My conclusion is that before evaluating the sine part at the boundaries, it says since the solution is unique, m have to be an integer.
Or n in our case. Or no? Yeah, you see, it depends on the boundary. You see.
Before evaluating at the boundary, we are computing on the uniqueness.
Well, you see, if we don't have the boundary, if we didn't have the boundary, I want this condition to be satisfied. Well, I want that condition to be satisfied, okay? Right? Well, that condition is satisfied if m is an integer. Now I have a problem. I said that m should be integer. At the same time, I said that m should be some pi times an integer, let's say. No, m should be integer. No, not pi times. But then I said that m should be pi over beta times an integer. So which one?
So beta is some bound to pi.
Well, I can choose this to be arbitrary, right? There is nothing that restricts a particular value of beta. Well, let's review some Fourier series. Suppose I want a function that has this shape. Okay. I can write this for x between 0 and L. F of x will be sum of a n of sine n pi over L times x. It is 0 at x is equal to 0, so that's why I only take the sine series. I don't add the cosines. Do you agree? Or I can say, let's say this is L prime, and this is my function. And then I can write the same function f as a sum over, let's say, bn sine n pi over L prime x. Of course, bn will be different. And in one of them, the sine is an integer multiple of pi over L. In the other one, the argument of the sine is an integer multiple of pi over L prime. Which one is correct? Both of them. You see, I'm only interested in this region. And both of the functions, both this expression and this expression give me exactly the same value in that region. Let me call this f prime. F of x is equal to f prime of x if x is between 0 and L. They have different also oscillator terms, but they're equal to each other in the interval that I'm interested in. Now, of course, f of x, if I apply it for values of x larger than L, will not be equal to 0. In this region, they are not equal. Well, in none of the other regions, they will not be equal in general. But nevertheless, in the interval that I'm interested in, they are equal. So let's go back to here. Do I want this property? Not really, not necessarily. You see, I already have a finite region of phi. I can say that phi will have values between 0 and 2 and this beta. So no problem. Now, this property arises if I allow phi to have all possible values. Because let's say phi is equal to 0 and phi is equal to, well, phi is equal to 0. I can just move my point as I wish. And continuously, I can come back to the same point, and it will be phi is equal to 2 pi. So if I allow phi to have any value, then I have to have this property. But in my problem, I can say that no, I'm restricting phi to be between 0 and beta. So there's no overlap. So I don't need this property if I first specify the region of phi. You see, if I allow phi to have every value, if I can change my point continuously. I mean, here I have a one point, which is along the x-axis. Phi is equal to 0. And if I just take it slightly below, phi will change discontinuously. It will become, let's say, 2 pi. So my function, the value of my potential at 2 pi and the value of my potential at 0 should be the same because I'm just changing my point continuously. But since I'm restricting my value already here from 0 to beta, I can lift this condition. I don't need to impose this condition. Because in my domain, as I move my point, phi will never change its value discontinuously. In my domain, phi just changes continuously. There is no such 2 pi jumps. No 2 pi changes. Now, if I relax this condition but require that my potential is 0 at the boundaries, then I come to this one, these possible values of m, not necessarily integers. And both of them should give me the same answer eventually. Now, if I use this condition, this one, now m is an integer. As long as m is an integer, this condition is satisfied. Then I have conditions on the boundaries. I have to impose the conditions on boundary to give additional constraints on my coefficients and delta m. Now, of course, in the book, it chooses this particular values of beta. For those particular values of beta, things are simple because if you set delta m is equal to 0, at those values of beta, phi is automatically 0 on the other boundary. So there's no reason to worry. But if I would be solving this problem for the general case, I would stick with this one. Any last questions? Okay, I repeat, I am expecting you to spend a lots of time on preparing the pre-reports. Well, the pre-reports are, in principle, they should cover the whole week. But if you kind of want to cheat, you can spend half of the time on the weekend, prepare the pre-report, and you have questions for Monday. And then, in the remaining of the week, you can prepare the other parts of the chapter. So you will have questions for Wednesday and Friday.
So when is the deadline?
Hmm?
When is the deadline?
You see, on Sunday or Monday, I think it's Saturday. On Saturday, I want you to to write down a prayer report. No, I corrected it. I should have corrected it, no? When did you check it now? Okay, so I had corrected it, let's say, a couple of days ago, but probably I didn't change it sufficiently. So it will be for, let's say, Sunday midnight.